So we are going to move now to the second presentation. I have to say that I have in this session two presentations given by outstanding students. As you know, that's those are papers that have been authored by a student or by a recently graduated student that they have also received a very high score from the reviewers. So we have two, and the first one is the one that we are going to have right now. It will be presented, hopefully I can find here, Mushtaq. So
Yes.
Please share your screen. Yeah.
Yeah. Yes.
There we are. So title of the paper is an adversarial optimization approach for the development of robust controllers. So please, Mohammed, you can go ahead.
Thank you. Thank you. First of all, I would like to thank you for giving us the opportunity to talk at this Evolutionary Conference 2020. This work is the direct result of my thesis, my master's thesis, which I wrote at the Honda Research Institute Europe, together with my supervisor, Tobias Rodemann. The structure of the presentation is as follows. After giving a short motivation, the investigated energy supply system and the implemented control strategy I introduced. Subsequently, I will get to the main subject, which is the identification of robust control strategies through the adversarial optimization approach. I will then present the evaluation of key results and finish off with a conclusion and an outlook. Starting off with the motivation, due to increasing use of electric vehicles, there's a rising demand for smart charging strategies to control the power flow between buildings and electric vehicles. Smart charging strategies are crucial for a reliable building power and charging power supply. And such systems as are depicted here, where we have a building complex, an integrated charging station, and also maybe some solar cell panels or integrated renewable energy sources are exposed to, these systems are exposed to uncertainty and dynamic environments. These uncertainties can stem from, for instance, from the charging behavior at the charging station, building power demand patterns, or also the weather. Of course, the weather can influence the power output of the PV power panel or the solar cell panels. So there's a major challenge for charging strategies or control strategies in this regard, which is to be able to cope with uncertainties and unexpected use case scenarios. The following goal can thus be formulated for our work, which is to identify control strategies which are able to cope with uncertainty and enable reliable and efficient energy supply in this regard. In the following, I will give an overview on the investigated energy supply system and the implemented control strategy, starting with the energy supply system. In our work, we looked at the system of a building complex with an integrated charging station, and this system can be divided into a supply side and a demand side. On the supply side, we have the PV power panel, which produces electric power, and then we have an external power grid which is connected to the system, which also serves as a power producer. On the demand side, we have a building power profile or a power demand profile for the building power for the building complex. Sorry, and in addition, we have an EV charging station, which is also integrated into the system. The stationary battery is also a key component of the overall system. The battery can be charged when there's excess PV power and discharged when power is needed. The overall system is modeled in Modelica as a simulation model, and the simulation model can then be used for objective functional fitness function evaluation during the optimization. The energy management strategy or the control strategy controls the power flow of the stationary battery as well as the power flow of the EV charging station. The control strategy is implemented as a rule-based control strategy, and it tries to mitigate peak power demand for the charging process and it also tries to maximize the self-consumption of the generated PV power. The control strategy is described as, or can be described via decision trees, where different operating modes are activated for different or for certain threshold values. For instance, if the building power demand exceeds a certain threshold value, the nominal charging power at the EV charging station is reduced. Both the control strategy as well as the system configuration or the energy supply system are parameterized. And in the next step, these parameters are to be optimized such that we can identify robust control strategies. The corresponding optimization problem can be described as follows with a Minimax optimization problem. Starting with the first row, we have an objective or fitness function, which is described with the maximum operator and a cost and reliability function, CE. Design variables are described through vectors, where vector X consists of parameters of the control strategy, and the vector S consists of the parameters for the model of the energy supply system. And these model parameters can, for example, be the building power demand or the nominal charging strategy, nominal charging power, or the maximum charging power at the EV station. These scenarios are called, these parameters are called scenario parameters in the following, and the vector S subsequently is called the scenario vector. And as you see here, the cost function itself depends on both on the vector X and vector S, meaning depends on the control strategy and the specific scenario in which the control strategy is evaluated. The restriction in this row mainly ensure the balance of the power supply and the demand. The goal of the robust optimization is a reliable and efficient energy supply, such that the control strategies can cope with uncertainties and also dynamic changes or dynamic behavior. Therefore, instead of designing the control strategy for a specific reference scenario, multiple scenarios are considered in the optimization, and therefore the Minimax formulation, which is depicted here, in each iteration of the optimization, therefore scenarios are sampled from a scenario set, and subsequently using the maximum operator and the fitness function, the worst controller performance is optimized over the whole optimization run, so that we can expect to gain robust control strategies over the whole optimization run. However, the robustness, the identified robustness is dependent and strongly dependent on the given scenario set. If this scenario set doesn't contain any severe or worst case scenarios, a worst case robust control strategy or worst case robustness is not guaranteed. And for our application, it is rather important. It's very important to enable a reliable energy supply at all times, even for unexpected or worst case scenarios. For this, it is necessary to incorporate these worst case scenarios or very severe scenarios directly into the optimization run or the optimization problem. And identifying these worst case scenarios for bigger and more complex scenario sets can itself become an optimization problem. And this is where the adversarial optimization approach starts. Here we have two opposing optimization problems, which are united into one overall problem. We have a minimization problem and a maximization problem. The minimization problem identifies, or let me start with the maximization. Maximization problem identifies worst case scenarios over the optimization run, and the minimization problem identifies corresponding robust control strategies. This adversarial optimization approach can also be understood from a game theoretic approach, where we have two competing players, the players being both optimization problems. In this work, evolutionary strategies are used to iteratively evolve and identify worst case scenarios on the one hand, and corresponding robust control strategies on the other hand. Therefore, a method used in the literature already is compared to a proposed method which we proposed in our work. Starting off with the method which is already used in the literature, which is the iterative co-evolutionary optimization. For this first method, the scenario and controller populations are evolved iteratively, as is indicated here, where we have an iterative evolution optimization, where the scenario population consists of the scenario vectors, and similarly the control strategy consists of the parameter vectors X. Starting with the current best individual in the controller population, which is in this example could be this one. In an iteration step, severe scenarios from here to here, severe scenarios are identified for that specific control strategy. And similarly, in the next step, for the current worst scenario in this scenarios population, control strategies are identified in one evolution step or optimized in one evolution step, which give a good performance for that specific scenario. Over the course or over the optimization run, we expect to gain worst case scenarios on the one hand and robust control strategies on the other hand. However, this approach can show a cyclic behavior where the control strategies are optimized for different scenarios, different use case scenarios, and start moving or jumping between local optima in the objective space without really advancing towards a global optimal area. So therefore, in this work, this archive-based optimization method is proposed. Here, optimization archive is utilized to store a diverse set of worst-case scenarios over the optimization run. The scenario archive is depicted here. With this approach, the previously identified worst-case scenarios are not forgotten, as was the case for the iterative co-evolutionary approach, the previous approach. Specific older scenarios or previously identified scenarios are specifically considered in the optimization problem. And with this approach, we can identify even more robust control strategies over the optimization run. To update the scenario archive in each iteration step for the current best control strategy in the controller population, a complete scenario optimization is done. And then using this scenario optimization, the scenario archive is updated. And this process is iterated over the whole optimization run. Moving further to the evaluation, I will now give an overview of the performance evaluation. For this purpose, first a fitness gap analysis is done, where a baseline controller and optimized controllers are performed and are compared, and both are tested against identified worst cases over the whole optimization run and random scenarios. The baseline controller is based on previous work at the Honda Research Institute and is a standard controller approach for our use case. In this table, you see in the first row, first of all, it is the performance of the iterative co-evolutionary optimization, so the method used already in literature. In the first row, you see the performance of the baseline, the mean performance of the baseline tested against the worst case scenarios and random scenarios, whereas we look at 20 optimization runs and the identified worst cases for the 20 optimization runs. The mean baseline performance here is indicated with 0.338, whereas this fitness value is a normed fitness value, which is normed between 0 and 1. 1 means very good performance, 0 means a very low performance. And the mean performance for the baseline, as indicated, is rather low, indicating that somehow severe scenarios could be identified over the optimization run. And the mean performance for the optimized controllers, which are identified with the co-evolutionary optimization method, is higher, especially especially we have to look at the difference, the fitness gap, which is here described as delta fitness, which is about 0.4. This indicates that the optimized controllers are more robust and perform better for somehow severe scenarios. And comparing this to the results of the archive-based optimization, we see in the first row, first of all, that the mean performance of the baseline is even lower, and we have a rather low performance. So this further indicates that this approach finds somewhat more severe scenarios. And on the other hand, if you look at the difference between the mean performance of the optimized controllers and the baseline, which is again depicted in the last row, the fitness gap, we see that with 0.6, about 0.6, the identified controllers with the archive-based optimization are even more robust in respect to the baseline performance. So we can say that with this approach, with the archive-based approach, there's a strong indication that we can, on the one hand, find worst-case scenarios, and on the other hand, by incorporating or not forgetting previously identified worst-case scenarios, we can even find more robust control strategies. The adversarial optimization is then further analyzed by introducing evolutionary trajectories. Here, as depicted in the diagram, we plot the controller fitness over the scenario fitness for the whole optimization run. So we gain a trajectory in the objective space. These evolutionary trajectories can give insights into the co-evolutionary dynamics of the adversarial optimization problem. First, we look at the evolutionary trajectory for the iterative co-evolutionary optimization, whereas again, 20 optimization runs are considered, and the curves in the background, the colored curves in the background, are the represented 20 optimization runs, and the dot marks represent the start of the optimization of a specific optimization run, and the thick blue line represents the averaged curve, averaged evolutionary trajectory over all optimization runs. As depicted here, in this approach, the co-evolutionary method tends to quickly reach a local optimal area where we have a rather high variance here in this convergence area, which indicates the cyclic behavior which we mentioned earlier. And comparing this to the evolutionary trajectories of the archive-based optimization, we see a different behavior. Especially, we see a proper search path proper search path is indicated in the objective space, where we have this search path or trajectory towards a more optimal area. Yeah? And here again, we considered older worst-case scenarios in the optimization run. Therefore, this search movement or search path is augmented. Also, the better convergence, which is indicated with the lower variance, especially for the scenario fitness, indicates that we identify more robust control strategies. Yeah, exactly. And I would now turn to the conclusion and the outlook. Especially with the archive-based optimization method, we could identify robust control strategies, and these robust control strategies are not only robust against the worst-case scenarios it was trained on, but also against random scenarios. And in addition, with the use or utilization of these evolutionary trajectories, a new perspective on the adversarial optimization topic could be given and could be reached. For further work, it is suggested that these optimization archives are further analyzed, especially looking at different sizes of the optimization archive to enable maybe a scaling of this approach for bigger real-world problems. A further analysis or investigation of the evolutionary trajectories is also suggested, which is to utilize the ET for evolutionary trajectories, for example, in the fitness evaluation or otherwise in the optimization progress, so that during the optimization progress, optimization problem, we can move better towards a global optimal area. And to finish off, this adversarial optimization approach has mainly been used on test problems or test functions in the literature. And with this work, we somehow did analysis on a real-world application and investigated this method. Thank you.
Oh, thanks a lot for your presentation. Also for being perfectly on time. A real interesting presentation. So we have now time for questions. Don't know if anyone in the audience have any questions. I saw that Bill Landon, you made a I'm going to read the question that Bill
okay.
is posing. It says domestic load may be weather dependent. For example, air conditioning or heating. External temperature can be predicted. Is there a scope for using weather forecast?
Regarding the weather forecast, because the focus of work was to investigate the adversarial optimization approach and apply this on a real world problem. Therefore, we in our work we didn't focus so much on the forecast. So we just use a simple standard building power profile, for instance, or weather forecast, the focus of the work was more on the method side, like applying the adversarial optimization on the real world problem. If I understand the question correctly.
Okay, yeah, seems so. I don't know if there is any other question from the audience. I do actually have a question and maybe also suggestion. Well, starting from the suggestion, I'm not sure. Maybe I skipped that detail in your presentation, but sometimes when you are using co-evolutionary algorithms, it's difficult to compare one approach to another one, because at the end the fitness is computed on the basis of some co-evolutionary measure. So it's not really directly comparable, because you are considering different test cases, so to speak, in each case. So I don't know if you have considered ones that you have used, or one that you have obtained your solution using one kind of coevolution or the other one, to use some kind of test set on which to evaluate your solutions.
We did not use such a test set. For us, it was more important to look at the difference, like look at the fitness gap, especially to see, okay, we have first of all, we would like to compare the baseline against the optimized controllers. For instance, here the co-evolutionary optimization, and look at, okay, what is the fitness gap, which indicates the difference between the baseline and the optimized controllers. On the other hand, we have the fitness gap for the archive-based optimization, and then this was like the main analysis we did. We did not have a specific test case, the test set. We said, okay, we look at the fitness gaps, which indicates that the robustness of the optimized controllers in respect to the baseline, this was our approach.
Okay, this suggestion or question was directed because the second question I had is that whether you are considering or planning to study in the future different ways of organizing or handling your archive. I mean, ways in which you can decide whether a certain solution should go into the archive or not. Because there are many different strategies, and of course, at the end, if you want to check whether one strategy is better than the other one, you have to look at the results and compare the different strategies on something that is objective, comparable. So that was the reason for my previous question, and then my second question is if you are really considering or studying the use of different archive management strategies.
This is indeed something was a crucial part in the work, to identify or to look at this update process. And currently, or in this work, we use the variance-based method. So our goal was to always have a very diverse set of worst-case scenarios stored in this archive. So if we, for instance, identify in a scenario optimization a scenario which is severe, but is very similar to an archive which is to a scenario which is already in the archive, we don't include it into the archive. We say, okay, we already have it. We don't, and we want a diverse set in this archive. And there, of course, as you said, there are different methods, and we looked also a little bit on different methods. But in this work, we used like this variance-based approach, where we really want to have a diverse set of scenarios in the archive. And for further work, this might be of interest. I would say,
Okay. So thanks a lot. Thanks a lot again for your presentation. It's a very interesting talk.